second speaker, I invite Maurizio Vretenar, that is group leader of CERN Next Ion Medical Machine Study. Please, Maurizio.
Yeah.
Good morning again. So I will speak about the design that we have made for SEEIST and new alternatives that are coming out in the last, they came out in the last year. First of all, as a kind of an historical background, it's already 6 years that we are working at accelerator designs for SEEIST and beyond SEEIST. Everything started for us, so we've seen from Sunny's presentation this morning that SEEIST started in March 2017. In June 2018, we had a very good workshop in Archon near Geneva, where we defined the first ideas and requirements for a new generation of accelerator for therapy with ions. We started a CERN initiative at CERN in 2019. We had some support from the European Commission by the so-called DLR contract to work with SEEIST, and we set up a collaboration to support SEEIST and in general to develop new designs for accelerators. We made this design converged into an application we made for the S3 roadmap in 2021 that was not successful. It was considered the project was not mature enough to be on the S3 roadmap. But the design, I think, was very solid, and you will see it later on. And then after that, we will continue working at CERN on different activities to go even forward beyond this design. Basic requirements are always the same. I mean, you know that carbon ion therapy in particular is very expensive. And so we have to make a machine that is smaller, less expensive, and also with better performance than the present generation of European facilities. And of course, on top of that, a new design must be easily industrialized, reliable, simple operation, reduced risk, accessible time to development, so SEEIST cannot wait 20 years to build an accelerator. So it's quite a complex assay environment. We started comparing 3 accelerator designs. So a standard carbon ion therapy synchrotron based on the PIMS design that was mentioned many times this morning, that you see the first one to your left. Then we explored the idea of a superconducting synchrotron and then of a full LINAC to reach the energy required for carbon therapy with a linear accelerator. The conclusion, you see here the matrix there, was that considering the needs of SEEIST, the conventional PIMS layout was the best, but please read the statement that we have. Okay, partly what you can read of that statement is that we recommended as baseline configuration the world magnet synchrotron, but the development of superconducting magnets should continue as an advanced alternative option. Because of its lower cost and smaller dimensions, it might become the baseline in case preparation for construction of SEEIST would take more time than foreseen. So we are in this configuration, and you will see in my next slides that we can go back to the superconducting design. What we have done for SEEIST was then to work to develop more this design with a conventional synchrotron, and it was a kind of a difficult work because on the one hand you want to do something which is innovative, which is new, which has better performance than anyone else, but on the same time you have to be conservative. So it will be something that can be built in the Southeast European countries, can be built by that does not require too much R&D for components. So this design configuration was a result of a very difficult trade-off between opposite requirements. But I'm happy that what we have worked out is something which is innovative for the idea that has to work for both treatment and research, has to provide 20 times higher beam intensity than the present European facilities, flexible extraction that would make possible flash extraction, and equipped with a linear injector, a LINAC injector that would also produce radioisotopes for therapy, radioisotopes, and for diagnostics. So quite innovative, but on the other hand, the conservative part was that it was still based on beams, which is known, reliable. It is being reproduced in two configurations, and is flexible enough for research. And then, in particular for SEEIST, we've been working on ideas of operation with multiple ions, multiple energies, and I don't want to go into the details, but an important point is that this was not a standalone facility. This was intended as the center of a hub. So the slide is not much readable, but around the main SEEIST facility, we had foreseen to have, possibly in another country, a structure for testing of accelerator components, a data center, a training hub, so really a network of facilities that would support the main center of the SEEIST. A bit some more details on the structure. Was quite in the tradition, in the line of beams. We have the main synchrotron, then the transfer line. We have foreseen 2 beam lines for experiments, three treatment rooms, 2 with fixed beams, horizontal and vertical, and then a superconducting gantry that in this configuration was rotating only from 90 to 180 degrees, and now has been modified for 360. So very nice, very big, 5,400 square meters. And this is what you've seen in the video that was shown this morning. So this is really SEEIST as a greenfield facility. And in fact, also accelerator can be seen here. The roof is removed to see the accelerator. But in this drawing, you also see that maybe it was too much of a greenfield. So there is nothing around this facility. And in fact, now there's only a forest. And in fact, now we should have conceived already from the beginning the SEEIST as part of something, as a part of a network with a hospital nearby, with so just in an environment, in a real environment. Yes, because at a certain moment, so we went after this S3 application, we have completed the written. We have completed a report detailing this design, and we said, how can we go forward? So this was a kind of a milestone for our accelerator design group that is centered at CERN but has many external collaborations. And then we started to think about where should we go now? So our decisions were based on on two considerations. The first is that carbon ion therapy, we have seen that there are many advantages, double strand breaking, and radiation-resistant tumors, as we have seen from the presentation this morning, but is not well perceived. Often carbon ion therapy is perceived as medicine for rich people, medicine for the wealthy. And there is a financial, psychological resistance to new carbon facilities. This is why we are not so many in the world. Only 3 ongoing projects at the moment worldwide for carbon facility. In particular, it is difficult to defend carbon ion therapy in countries that are not yet equipped with a large number of X-ray conventional radiation therapy facilities and not with proton therapy. So to make the jump from a small number of conventional radiation therapy to carbon ion therapy, it's a bit too much. This was our consideration number 1. Consideration number 2 is that also one of the problems was that somehow it was a big investment that had to be taken from the very beginning. So it was very difficult to define the SEEIST for an implementation in small stages. So you could do in some stages, so you could start with a LINA, but then you had to build a big synchrotron. That was a big part of the funding. So, and it is difficult to go to the politicians to say that, so give me from the very beginning a large amount of money to build something in a place that has nothing, where there is not a community, there is not an industrial background, there is no experience in accelerators. So we thought that the problem is not only technical, it's also politically. So you have to somehow to conceive technically what you propose in a way that it can be built in stages. You know, politicians, they like to cut ribbons. And the more ribbons you give them to cut, the more they are happy. And this is why we said, okay, how can we conceive a facility that also is compatible, let's say, with the political environment? And then we went to we exposed some alternatives at lower cost that could be implemented in stages, and we can do a compensator for proton and helium. So we jumped on helium because helium is between protons and carbon. For the moment, it's not yet licensed for therapy, and Heidelberg is working hard. I hope that Sami will give us some more details on where you are with the licensing for helium. And Heidelberg has been the pioneer for to widen the use of helium for therapy. Helium was also used in Berkeley for many years. Yes, and the accelerator is much smaller. It's much smaller because the ion is lighter, so you need less energy to reach the required penetration with helium. And you see that the bragg peak is some protons and carbon, so it is much sharper than protons and doesn't have the fragmentation tail of carbon. So, and also on the other side has a very reduced lateral scattering with respect to protons. So it's a big step forward in terms of conformality with respect to protons. Might have some of the advantages of carbon also for a recent tumor, but it's not yet proven. I mean, it has to be completely explored, and could be a kind of new frontier for particle therapy. So this was just basically, this was based on the initial work at Heidelberg, but what we have done, we have developed how would it look like an ideal accelerator for helium. And we came out with the design of a triangular synchrotron that you see here, which is only 11 meters on the side, is the main dimension, with an accelerator that is a bit larger than what you need only for helium, because we want to reach the energy to produce alpha meters for targeted alpha therapy. So this is, let's say, what we have designed. It was also helped by the fact that at CERN we have some experience in building small synchrotrons. So it was quite easy to achieve. So this is the latest three-dimensional drawing layout of this triangular synchrotron with the magnets, the RF system, and all the components in. It was relatively easy to make this design because we have built a few years ago a small decelerator of antiprotons that you see to the right, which is that machine there. It is called Elena, and it's interesting because just changing a few elements, you can go from a machine that is designed to decelerate antiprotons to a machine that is designed to accelerate helium for particle therapy. So it's not a big jump, let's say. It's always a synchrotron, and the number of magnets is the same. And you see here the dimensions, the person in the middle, and this is the dimension of the machine. So it's also relatively easy, let's say, to make this design. And the advantage is that we can really have a staged approach, because you can start, first of all, building the ion source and the injector. It's going to be a test stand. It's not going to be used for treatment, for any medical application, but would be the first stage. The second stage would be the real accelerator for production of medical radioisotopes. And this would be already allowed to do to produce isotopes and to start some research and possibly also some treatment, for example, with alpha emitters. So this LINAC, but you will see in the next slide some more details about this LINAC. Step number 3 is the synchrotron. The synchrotron is smaller, so it's not a big investment. And the synchrotron can start, first of all, operation for research, then can start operation with protons, then you can go to helium. You can start treatment, first of all, with the fixed beams, then install possibly a gantry or a chair if there is not enough funding to build a gantry. By the way, I forgot to mention that we also have foreseen that with this synchrotron, you can go to higher energy than what you need for treatment with helium to do also radiography with helium. So the idea is, first of all, that you scan the patient with a low intensity, higher energy helium beam, and then the next pulse, you do the treatment with helium. So this is what is foreseen with this machine. It's not a dual beam, but it's just into different pulses. Then you have but then we can think to the next step, that is step number 6. So the same design, if you just change the magnets and you go to superconducting magnets that allow you to go to a higher field, then you can go to carbon. So the same design, the same lattice of the accelerator can be used for a superconducting synchrotron that would go up to carbon. And this is the basic design that is being prepared for the last deliverable from our work package in He3+ by Elena Benedetto and her team. And this is, I think, an excellent opportunity for SEEIST. Because now we are in this moment, large carbon therapy facilities are becoming commercial. So now Mayo Clinic has signed a contract with Hitachi for the construction of a carbon therapy facility. IBA is building a carbon therapy superconducting synchrotron for Arshad in Cone. So it will be difficult to defend that SEEIST will go to another different design. We spend a lot of money to develop, to industrialize a new different design. Instead, there is, I think that the perspectives are good to go to explore a superconducting design based on a new generation of magnets, because also in Japan, the HIMAC team is also working at a superconducting synchrotron for carbon using, let's say, conventional superconducting magnets. Instead, in He3+, we have worked a lot on a new type of magnets it is called canted cosine theta, that would offer, let's say, many advantages in terms of cost with respect to conventional magnets, but also I would really like to explore hybrid magnets. Often called superferric superconducting magnets that are kind of low-cost magnets that could operate at higher temperatures and could, for example, only be cooled with nitrogen. Nowadays, to get helium for superconducting equipment is very, very, very difficult and very expensive. In the future, it's going to be even worse. So superconductivity that can work at higher temperature is really the direction to take for the future. So I give you the idea. So please think about it, and we plan after this work that we're going to do in He3+ to continue in this direction that I think is very promising for particle therapy. I have only a few minutes left. One last point, the LINAC for the isotopes. Our goal is to use the helium beam because we accept for helium. But helium, when you say helium is alpha particles. And a beam of alpha particles can be used if the beam is sent on a target to create alpha emitters. And alpha emitters, like astatine 211, are perfect for targeted alpha therapy. There are many clinical trials ongoing on therapy of cancer and also of diffuse cancer with alpha emitters. And there might be in the future a strong demand for astatine that the present generation of accelerators is not able to fulfill. So if we come out with a design that can also produce astatine, with something that really it's a way towards another dimension of nuclear medicine, the dimension of therapy and diagnostics, because also the astatine also produces some electrons and positrons that can be detected, so you can know where to deposit your dose. So last two slides, potential users. So for this helium facility, we've already two potential users. One has been mentioned by Manjit, which is the Advanced Particle Therapy Center for the Baltic States. So that this is the other side of the Baltics with respect to Stockholm, because it's Latvia, Estonia, and Lithuania. And they are interested. And first of all, before starting this work, they have analyzed what they have in the country. So they have enough X-ray machines, but they don't have proton therapy. But they don't have enough patients to justify a carbon ion therapy. So this was their argument. So really, there are not enough radio-resistant tumors, let's say, in the region to justify carbon ion therapy. And then there is interest from Switzerland, pushed by Ugo Amaldi and the TerraCare's new foundation that is going to propose this one for Switzerland. Anyhow, at CERN we are working to accelerate designs, and accelerator designs are available to everyone, and everyone can take the design. So we are again in the situation of the toolbox. Everybody can take the parts of the toolbox and build their own facility, and then negotiate with CERN for technologies. We are open, of course, and thank you for your attention.
Thank you, Maurizio, for this important focus on technology, evolution of technology. Again, please, question.
Yes, Maurizio. It is a and it was an excellent talk. I could follow really many things. I have a couple of questions. As Angelica maybe mentioned, and the colleague also from now, the difference between, let's say, protons and carbon is the radiobiological effect. Yes. Do you have any sign about this or a figure about the difference between an alpha beam and a carbon beam? Do you expect the same effects? I mean, efficiency, so to say?
Efficiency, yes. So in the sense that definitely helium is better than protons in terms of probability. Yes, it's comparable to carbon. It's comparable to carbon because the black beak is not as sharp as carbon, but you don't have the fragmentation tail. So I would dare say that it is comparable to carbon. And then from the point of view of resistant tumors, it's not demonstrated, so we don't have enough data.
Okay. Now let's say the next question is the following: if you build what you propose for alpha,
yes,
can you do that? I mean, can you use protons with this?
Yes.
So, assuming you have the money to start with protons, then you can switch to helium.
Yes, sorry, maybe I was not clear enough. The idea is to start with protons. First of all, you start with protons, and then you commission it with the helium.
And what is the cost of this machine? And I'm done. Thank you.
No. Make your own extrapolation. So this, you know how much is the cost of a proton therapy system, and you know how much was the cost of SEEIST. Take something in between.
So 120.
For example, and it also depends on how much you want in terms of additional features. You want to raise isotopes or not? You want 3 rooms? You want 1 room? So it's like when you buy a car. I mean, the cost of the car is very small, but it depends on how many accessories you want to your final price.
Thank you.
Yes, Maurizio, I'm sure it is the case, but please confirm. CERN is not patenting any solutions from the accelerator. It's just giving free to those who wants to get it, or you patent it, and there are some legal way to get the technology.
No, it's a good question. Our technology for hadron therapy is free and available to everyone, but in priority to member states of CERN. So we work for the member states of CERN because they pay for CERN, so it's their, let's say, property, what we do. And even when CERN makes patents, they usually give free license to member states. Those who might have to pay for patents are companies or non-member states.
Another one, please.
So I have a question, Maurizio. A nice talk, of course. My question to you, of course, staging is really, staging procedure is very great. And also you gave a good example for politicians why this is important. But now restricting, actually going to the smaller size, going to reducing the price, the factor of 2, as you mentioned, and restricting ions to only proton and helium. Are you at the same time restricting the research possibilities? Because I want to underline that SEEIST was supposed to dedicate 50% time to research. And we count on EU funding. The large fraction from EU funding could not come if you don't really provide like a really large spectrum of the research possibilities. And this is now my question.
Yes. More than the question is a remark, an observation. Yes, you are right. In the sense that the original idea of SEEIST was also even to go beyond carbon to oxygen, for example, to research with oxygen. Definitely, this is something that probably is not going to be possible. But on the other hand, you can make any type of ions at lower energy, even for a smaller machine. So the point is that you don't need to have the energy for the 30 centimeter penetration that you need for treatment. You don't need if you do research. So if you add some additional ion sources, in principle you can make research. You make research with a type of ions, but you cannot make treatment.
Okay, last very short, please.
So I just wanted to make a comment to Sotiris. The advantage of helium over protons is not only biology. There is a big advantage in the physics because it's a much heavier particle. Because it's a heavier particle, it's much harder to scatter. And this gives us a depth advantage that we don't have with protons. As we go deeper, the protons smear, they give us a problem on the edges, and we cannot control the fall off really well. So there's the biology and the physics. And these two parts are critical because they go hand in hand.
You understandable. Thank you so much. I thought as a politician, not as a physicist.
Okay. Okay. Thank you, Maurizio.